morning and welcome to another CWS seminar. It's my great pleasure to introduce our speaker today, Dr. Milad Latifi. Milad is going to talk about from data to insight, machine learning models for predictive asset maintenance in water systems. This was part of a collaborative project with Data Techniques as a KTP project, which we did for last 3 years, and it finished at the end of September. Milad is currently working for Data Techniques, so over to you, Milad.
Thank you very much. Great. Good morning. Some of you may have been seeing me doing some kind of physical experiments in the lab, pressurizing the pipe and blowing the pipe, making bursts in the pipes. But that was one part of my knowledge transfer partnership project, KTP project. And today I'm going to talk about another strand in my KTP project, which is about how to use data to obtain insight about water distribution networks and how they fail, how the pipes are going to fail, and how we can define or develop predictive asset management approaches in the water pipelines. For the first part, I'm not sure you have played Mafia or Citizen. It's like a game. All the players are split into Mafia and Citizen groups. Mafia know each other, but Citizen don't know each other. They have to talk with each other and try to find out who is Mafia, who is Citizen, and try to kill the Mafia. If the Mafia kills all the citizens, Mafia wins. But if the citizens want to win, they have to try to find out who is Mafia and who is Citizen and try to kill the Mafia. So why it is similar what we are doing here today, I'm going to delve into it in a few minutes. Good. So, is all right? Yeah. So, we all know about the failure. When a pipe fails, it's like a hassle for everyone. For the water utilities, it has a lot of cost. They have to come in, dig the ground, replace the pipe, or fix the pipe, and then backfill the soil, return everything, recover everything. It's a hassle for the customers, consumers. They have a downtime. They actually a break interrupts their water supply, and also it can waste a lot of water. It can pollute the environment. It can things like that. So, what factors affect the failure in a water pipe? We can categorize all the factors affecting on failure in 3 categories. First is pipe intrinsic factors like pipe age, material, diameter, length, any existing defects in the pipe, things like that. Environmental factors like climate, soil, and everything surrounding the pipe. And how we operate the pipes, like any pressure management schemes in place, or the history of transient events on the pipe, any kind of cyclic loading on the pipe, things like that. How to deal with failures in water pipes and how to do asset management in water systems. Traditionally, we do reactive asset management, asset maintenance, which means that we wait until a pipe fails and then we can go and fix the pipe, which is too late, and as I have mentioned, it has a lot of expense and cost for everyone in this ecosystem. Next approach is preventive approach, which means that we can replace the pipes based on some characteristics of the pipes, like age, material, things like that. For example, we can go, I'm going to replace all the asbestos cement pipes older than a certain age. In that case, it's quite possible that we are going to replace the pipes which can still work for another 10 years, which means that it's too early to replace the pipe. It's a waste of material and budget. But the most recent approach is predictive asset maintenance, which means that looking at the pipes based on their condition and predict when the pipes are going to fail, or predict the likelihood of failure of the pipes in the future, or predicting the remaining useful life of the pipes. In that case, we can go and replace the pipes just on time, right on time. For predictive asset maintenance, there are a wide range of approaches or tools or models from old times. These tools were proposed to predict the likelihood of failure in pipes or remaining useful life of the pipe, like physical models, which look at the factors affecting on pipe failures, like pipe corrosion, freeze and thaw, or any kind of loads or soil pipe interaction, which makes the pipe fail. But newer models, like statistical models, can be categorized into deterministic, probabilistic, and machine learning models. In our research, we have focused on machine learning approaches, machine learning research. And I'm sure most of you have worked with machine learning models, you have developed machine learning models, but I'm just going to talk about machine learning models in 1 or 2 minutes. We need to collect the data, we need to cleanse and prepare the data for training a machine learning model, and then we can train a model. It can be any kind of machine learning model. And then we need to validate the model, and at the end we can improve and then come back and close the circuit. I'm sure you're quite familiar with different kinds of machine learning models, like unsupervised modeling, which doesn't have any kind of label or target to predict, and supervised models, in which we have to predict a target or a label for each instance. We have classification and we have regression. In classification, we have to put each instance into predefined classes or groups. But in regression, we have to predict a value, a continuous value for each instance, for each new instance. And supervised learning is something like this. You can have a set of, for example, apples and oranges, and you can train a model to learn what is an apple, what is an orange, and for the new instances, the model can predict or identify which instance is apple, which instance is orange. This is just a very simple overview on the machine learning models. And what features help us to do a prediction in supervised learnings? For example, if you have a water distribution network, if you want to predict a failure in water pipes, we may have features. Features could be numerical values. They could be like categorical values. What kind of categorical values, in a water distribution network, in the datasets of water pipes? Like material. Material is a categorical value, or any other categorical value, Flow rates? Yeah. Soil type. If you have soil type data, that could be like a categorical value. And also the features, the data that we can get from water utilities could be like time series data, flow, pressure, or anything else. And the target to predict could be something like failed or not failed in the future, or in the past, here in the past. Or it can be something like time between failures or things like that. So if the problem is about predicting fail or not fail for the assets, we can have a binary classification problem. And the machine learning model should predict between these two factors, between these two states, actually. And what features are available from water utilities to predict the failure? Most of the time we have diameter, length, age, material. Depth is not always available, and in the cases that the depth of installation of the pipe is available, it's not very reliable, because when they were installing the pipe, it's not usually common to measure the depth and record it somewhere. region or area, how it is impactful on failure, how we can use region or area of installation of the pipe. In the cases that we don't have any data about the soil or whether it can serve as a surrogate measure instead of soil or weather data, so region or area can also be useful. Pressure, maximum pressure, history of maximum pressures, and also the difference between minimum pressure during the day and maximum pressure during the night can also be useful for predicting the failures. Flow and velocity as well. Velocity is a function of flow. That could be useful to predict the failure, and we found out that the flow is also impacting the failures. Soil and weather, these are the factors which are not always available, but if they are, they could be really useful. And machine learning models, we have a wide range of machine learning algorithms which have been developed for predicting things in different branches of science. In this research and in this set of research, we have used decision tree algorithms, which I'm going to talk about them in just a couple of slides. A decision tree is something like this. It's like a tree, and when the tree is developed and trained, and you have a new instance, you can go to the tree and ask about that instance from the tree. A tree asks you, for example, is the pipe a main? You have to answer yes or no, and then in the next level you have to answer other questions. For example, if the pipe is older than a certain age, or if the pipe is longer than a certain length, or things like that. And after, at the end of the day, the tree can identify whether a pipe is failed or not failed. This is a simple illustration of a tree. But decision trees, although they are easy to develop and they are easy to use, they tend to overfitting or some other problems in data science. But we have some other ideas to make models better predictive for failure in pipes, or in any other branches of prediction. We can, for example, bagging the models. We can have different subsets of assets and make weaker models rather than having a model, a tree which predicts everything. And then at the end of the day, we can actually have a voting between all those weak trees, weak models, to find out the final prediction. A good example of bagging is random forest models. We can have boosting. In boosting, we develop a tree or a model, and then we evaluate the error. In the next step, we try to make actually make some modifications in the tree to reduce the error. And in the next step, we reduce error until we can get a model with least error. But at the end of the day, we make the prediction based on all the trees that have been made in this process. Extreme gradient boosting and categorical boosting, XGBoost and CatBoost, are examples of boosting approach. And also we can have stacking approach, which looks at different kinds of models. It doesn't need to be exactly decision tree or random forest or things like that. It can be neural networks, support vector machines, or any other machine learning algorithms. And after developing all the algorithms, we need to have a meta model which averages all those models by different weights and make the final prediction. And to make sure that the failure prediction model is working good and predicts well, we have some indicators. For example, if we have a regression problem, we may use mean squared error, root mean squared error, mean absolute error, or even R-square. In classification, we have precision, recall, accuracy, specificity, F1 score. I'm going to talk more about this part in 1 or 2 minutes. And if you have a ranking, for example, a ranking of likelihood of failures for pipes, we have other indicators or measures to evaluate how the ranking has been done good. But mafia or citizen, if I generated a failure prediction model and it gives likelihood of failure for all the assets, and I sort all the assets based on their likelihood of failure, the highest at the right-hand side and lowest at the left-hand side, and if I want to replace the assets, how I should go and replace the pipes based on the likelihood of failure, because I don't know which pipe is really failed or not failed. If I just pick the first one, the first instance, the accuracy of the prediction is 100%, but I only found the first one, not and the 9 other failures were not captured. If I am a bit brave more, and if I replace 2 assets, or if I predict 2 instances, the accuracy is 50%, and I'm still predicting 1 instance correctly. If I go further and replace, for example, 4 assets, 3 are correct and 1 is incorrect. The accuracy is 75%. And if I go further, for example, if I replace 25% of the assets, I can capture half of the failures, because here I have 10 failures, I've captured 5 of them. Accuracy is 50%, but in this case I've captured more failures. And if I go further and replace, for example, half of the assets, 50% of the assets, I can capture 80% of the failures. It means that to make sure that I can capture more failures, I have to spend more money, spend more budget, and I have to be brave to take the responsibility for mispredictions. Actually, these instances are mispredicted. And at the end of the day, if I want to capture all the failures in this data set, I have to replace 75% of the instances or the pipes. So it's not easy to shoot someone and say, this is mafia or this is citizen. So we have different indicators for measuring how a failure prediction model or a prediction model is predictive in binary classification. If I predict someone as positive and it's really positive, it's a true positive. If I predict an instance as negative and it's really negative, it's true negative. But the problem starts when I have predicted something as positive, but it's negative, which is a false positive, and also I can false negative. And the next step, I can have precision, which is the ratio of true positives to all predicted positives. I can have recall, which is the ratio of true positives to all actual positives, and also the accuracy, which is the ratio of all true predictions or correct predictions to all the instances in this case. These indicators or these metrics have been developed for most of data science problems which use binary classification. But it's very important to know how they're useful for our problems. There are other indicators like ROC, receiver operator operating characteristics, or F1 score. F1 score is a harmonic average of precision and recall. I'm not going to delve into all these metrics. In one of our papers, we have an appendix which details all the evaluation metrics for failure prediction in pipes. But when the problem starts, this confusion matrix looks like we have, for example, 50% of the assets as positive or failed, and 50% as not failed. But the problem starts when we understand this is the problem, or even worse. In most of the cases that we have worked on, in the case studies that we have studied, the ratio of failed assets to the whole assets, or to the entire data set, is something between 2% to 5%, to 7%. This is because we have short period of all the failure records. And if you have, for example, 2 years, 5 years, or even 10 years of failures, it doesn't give you enough instances of failures. So in this case, for example, if you have a data set of assets which have, for example, 5% of assets failed, and the model predicts all the assets as not failed, what is the accuracy? 95%. The accuracy is 95. You have only 5% of not failed assets, of failed assets. Model predicts all the assets as not failed, and accuracy is 95%, and it predicts nothing. This is why these kind of metrics or indicators are not very useful in highly imbalanced data sets. Let's come back to the likelihood of failures and the indicators the other problem that we have with those kind of indicators is that precision, recall, accuracy, they are not very easy to translate into water utilities language. So they cannot understand what they have to do, what they will obtain by replacing these set of assets or things like that. So we proposed a new indicator which is captured failures by each replacement percentile. For example, if I have 5% of the assets replaced, actually I have random likelihood of failures for each asset, random scores for each asset, I expect that, for example, if I replace 10% of the assets, I get 10% of the failures, fine. But if I have a model which predicts likelihood of failure based on the real failures, and it's a good and predictive model, I expect to find more percentages by replacing a given or a specific percentages of the pipes replaced. So, for example, if I have 5% of the assets failed, I've captured 10% of the failures. If I go further, if I replace 10% of the assets, I've captured 30% of the failures. This is something that makes sense to the water utilities. They can find out by what amount of budget or investment in their assets they can capture more failures. And then we can go further by replacing 25% of the assets. This is the size of investment in assets. We can find out, for example, 50% of the failures, which reduces the number of failures in the future years. It can go further and further. Considering a annual replacement rate of, for example, 1%, I know that it's actually not realistic, at least in the UK, but in some countries we have 1% of replacement in the water distribution networks. Having 1% replacement in the assets, anything below 2 percentile of the assets replacement is like short term. It can be done in 1 or 2 years. Anything between 2% to 10% can be done in less than 10 years. And anything over than 10% of replacement of the assets can be done in strategic plan. So in this way we can talk to water utilities about what amount of investment can bring you this amount of failure reduction in your network, or it can reduce the hassle in your daily job. To make sure that the suggested models are working well, we took some case studies from different countries, a water distribution network in the UK, from water utility in the UK, all the assets. Another case study is from Australia, a city in Australia, and a city in Spain. We had data from 3 years to 12 years of failure data, which gives us different levels of imbalance data. And in the following, I'm not going to talk about which approach has applied to which case study to make it, to keep the anonymity. And what are the challenges? Most of the challenges that we have starts from getting data. In most of the water utilities, they have all the failures recorded, but the digitized part of the data is still short. They have started to digitize all the data in recent years, and most of their data is still on the paper, even in the UK. And we have incomplete or unreliable data. We have low resolution data. Also, we know that there are some factors affecting on the failure, but we don't have access to those kind of data. For example, we have all the pipes buried in the soil, and soil is a really important factor on the pipe's failure, but we don't have access to soil data. It's a big shortage of data here. And in the cases that we have augmented our data sets with soil data, we have seen the improvement in predictions. We have imbalanced data sets, as I've showed you, and also we have various data types like numerical, categorical, and time series data, which necessitates a multimodal machine learning model, or needs to simplify the data to be able to be used for traditional machine learning models. And to overcome these kind of challenges, we propose some initiatives, and in the remaining minutes I'm going to talk about these initiatives and how we applied them in the case studies and what was the results. First thing first, we find out that there is a good approach of clustering the assets. For example, if I have all the assets, all the data sets, all the pipes, and if I develop a machine learning model to predict the failures in all the assets, it works in some way. But if I cluster the assets into some categories, for example, if I put all the pipes with similar characteristics in one cluster and others in other clusters, and if I develop or generate or train a machine learning model for each cluster, it actually yields better results, better predictions. This has been done before we start working on, but we suggested to do some kind of clustering based on domain knowledge or domain expertise, which means that, for example, if we have a cumulative number of failures for all the assets, and we illustrate it as a function of the age, we can find out some clusters in the assets. If we cluster all the assets based on these different categories or different groups, and then cluster them by traditional approaches like k-means clustering, we can get better results. And these are actually some presentations of how the clustering happens. For example, we can have 3 clusters, we can have 7 clusters, and on each cluster we have trained a specific machine learning model. This approach yields better results than having a machine learning model for entire data set. The other problem was the imbalanced data, dealing with imbalanced data. When we have imbalanced data, for example, here, the red dots present the failures, and the purple dots are not failed assets. Here we have 7% imbalancedness, and how to deal with them, how to treat the imbalancedness in data sets. There's some approaches. For example, if we have a minority class and a majority class, we can eliminate some samples or remove some samples from the majority class to a balance level, which means that we have the same number of instances in minority class and majority class. Or we can generate some samples in minority class by simply duplicating the instances, or by generating or interpolating between 2 existing samples in this space. We can generate new samples for minority class to the level that we have balance level. We have enough number, the same number of instances in minority class and majority class. Actually, these are the traditional way of dealing with imbalanced class data sets. And also, we suggested to, at the same time, oversample the minority class and undersample the majority class at the same time to a balanced level, or undersampling to different levels or oversampling to different levels to see at what level we can get the best results. It's a bit different from the traditional way of oversampling or undersampling. In addition to that, we have class weights. For example, if we have a minority class and a majority class, we can give a weight of 4 to the minority and a weight of 1 to each instances in the majority class. In this way, the model has an incentive to find out the minority class instances. We propose to use variable class weights to find out at what weight we can get best results. And we find out that when, for example, in undersampling, we move from completely imbalanced data to a balanced data set, we can get best results somewhere in between, not exactly at the balance level. And the important thing is the trend of train dataset and validation dataset are very similar to each other. For example, if I find out the best level through the train dataset, I can use it for the validation as well. And the same behavior has happened in the machine learning models which are developed by SVM. And again, in undersampling with different levels, we have seen the same behavior by moving from completely imbalanced data to a balanced level. We have seen the best results somewhere in between, not exactly at the balance level, which gives us better predictions. Even in oversampling, we have best results in the middle, and we can capture more failures when we take the minority ratio somewhere in between, not exactly at the balance level. And by changing the class weight, this is the balanced class weight. This is the actually the weight of 1 to each sample. And when we move from imbalanced class weight of unit, to the best class weight, the balanced class weight, again we can see that the best results happen somewhere in between. In this way, we can improve the prediction capability of the machine learning models to predict more failures in the future. The other approach that we suggested in one of our papers was to make ensemble of weaker predictors. For example, if I have 8 years of train set, I can split that 8 year into 7 2 years, or 6 3 years, or 5 4 years of data, and then which gives me, for example, 28 splits of data. And also I have 4 machine learning models. I can have 112 predictors, which are not exactly the best predictors, but they are predictors with different capabilities. And in next stage, we tried to stack these models or ensemble these models using the verification dataset, which was only 2 years. We tried to find out what is the best weight for each predictor to be ensembled with other predictors to give the best results. For example, we just ensembled the predictors with the same number of years, only 2-year predictors, only predictors trained on 3-year datasets, etc. Then we tried to stack the models based on just with the same machine learning model, SVM, logistic regression, random forest, or XGBoost, and we tried to stack them. And at the end of the day, we tried to stack all the predictors, but not 112. We tried, for example, 20 of them, 30 of them, 50 of them, and see at what point any more predictors does not improve their predictions. Even in this way, we have seen that ensembling or stacking weaker models can yield better results than having a single model for all the assets. Next strand was getting climate data. For example, in one of our case studies in the UK, we tried to get data from Metafis and try to find out different climate factors, climate variables for each asset. And we have augmented our data set with climate data like precipitation, temperature, freeze and thaw factors, drought indices, etc. And even this approach have improved the quality of the predictions. In one of our case studies, we had limited data of soil, just backfill soil, bed soil, and even when you can see, although we don't have a good distribution of backfill soil, 70% of the assets are laid on the soil with the same type, with the same class. Although this is not very good distributed, but we got very good results when we augmented the data sets with soil data. And yeah, I can show you when, for example, we had climate data, the augmented models have predicted better than the baseline models, and having augmented models added precision, recall, and a fund score, and even, for example, if we have different percentages of pipe replacement, for example, 1%, 2%, and 5%. In some cases, we have better predictions by augmented models. And the last thing was working on service lines. In some countries, the water utilities are responsible for service line pipes. So any failure or any leak in service lines should be fixed by water utilities, and they have an asset management plan for replacing the pipes, replacing the service lines during the year. But they do it with a reactive approach, like what I have mentioned at the beginning of the presentation. They wait until a service line starts to leak and then they go and fix it, or they replace it based on, for example, on the age of the service lines, service lines, or they replace all the service lines in the street, things like that. For the first time, we proposed to use a machine learning approach to predict which service lines are going to fail in next year, in next 5 years. And the results, although the data set was a bit short, but the results show some improvements in predicting. By having 8 years or 9 years of data, we can see, for example, by replacing 1% of the service lines, we can reduce the number of failures by 2%. By replacing 5%, we can reduce the number of failures by 8 or 8.5%, and more. So, I'm going to talk about the future directions for what we have done. First thing first, over the past 3 years, we were challenging with access to the data. It's very difficult to get data from water utilities, even anonymized data or data which have changed or distorted. It's not easy to get that kind of data. So one of the ways could be developing some benchmarks for failure prediction with enough data, enough failure data, enough number of pipes or assets, and putting them on open source repositories for the use of researchers. The other strand for us is to utilize the live sensor data, which is a part of my KTP. The project that I've done is about installing different kind of sensors on pipes to monitor how the pipes are behaving, and feeding the machine learning models with this live data for them to be able to predict when the pipes are going to fail and what is the remaining useful life of each asset. The other strand would be integrating physics-based models like digital twins in my KTP, we have developed a digital twin of soil pipe system, which can be implemented in real world. Having enough number of sensors on the pipes, we can monitor the strain on the pipe, for example, or other factors, and see how the pipes are responding to different kind of loads, internal pressures and external loads. And we can integrate these kind of physics-based models with AI models. This is what we have done, and this can be integrated with data-driven models. Next strand is application of deep learning, which is quite common and buzzword these days. LLMs, large language models, we can use them for making the job easier for asset managers and operators in the water utilities. And also, we can use the AI decision-making assistants for making better decisions. And at the end of the day, we need to have smart water distribution networks. But it seems like to be too early to say that, but by starting to install sensors and monitoring everything in the water distribution network, at some point we can obtain the smart water distribution networks, which makes everything easier for us to manage and control and invest. These are a set of future directions for us. Thank you, and thank you for your attention.
Thank you very much, Milad, for a very interesting talk. Any questions? Yes.
Thank you so much for your presentation. And you just mentioned about the approach to tackle with the imbalanced data. I just have one question. So, is it possible to increase the accuracy by, like, making sub-classification in the pipe that has no failure?
Actually, if the dataset does not have any failure, the machine learning model cannot identify between fail or not fail. We need to have from both classes in our dataset to train the model.
Yeah, I mean, so you got all the input data that includes the failure pipe and the pipe with no failure. They have like distinctive features, difference. But what about in the, because there are more data in the pipe that have no failure, do they have the consistent features, very similar features?
I'm not sure it's a good way to train a machine learning model, because when we have a data set, as I have showed you, when we have a lot of not failed assets, yes, and just a few samples or instances of failed assets, the model tends to predict nothing.
Yes.
And it's not a good way to
so I mean,
sorry, is the question that feature importance, is that what you are asking? Which features are causing more failure than others?
No, I mean just sorry, let me see. So is that making classes in the healthy pipe like will increase the prediction accuracy? I mean.
Not failed pipes, you mean?
Yeah, I mean, probably. So the failed pipe shares some similar features with some classes of the pipe that have no failure. So is that like detection of that will increase the prediction accuracy?
No, to the best of my knowledge. And the classification is about distinguishing between two different classes.
Yes.
If you don't show enough instances from one of the classes to the model, it cannot learn how to identify this class from the other one, even it is majority or minority. If I have two classes, I have to show enough number of instances to the model to learn how it should work. For example, if you are growing up a kid in your home, at your home, and you don't let him to go out and play in the street or things like that, you don't know, or she don't know how to deal with dangers in the street or things like that. You have to show it the different instances, different problems, and then it can predict.
So if I understood your question, I don't think we have a cluster that it has got characteristics that they haven't contributed to the failure. So we can't say, for example, these pipe diameters, these ages, these material never failed. The combination of those have resulted into failure. So yeah, it's very difficult to find a cluster that has never failed. Some characteristics, features in that cluster has contributed to the failure. I think if I understood your question, it was like a cluster which hasn't contributed at all to the failure. We don't have such a thing. For example, we may have failures in young pipes, we may have failures in old pipes, different material, different diameter sizes. So there will be element that has contributed to the failure.
Thank you so much.
Following Raz's answer, these are the clusters for us, different clusters. For example, here we have 7, 8 clusters, and none of the clusters have not failed assets. All of them have failures, so we cannot have a cluster which doesn't have any failure.
Yeah.
It's not easy to find that cluster.
Yeah. Yeah, because it's very complex interaction between different features, so it's very different. Any other questions? Yes. Yes, please.
What's your definition of a pipe?
It's a good question. Actually, when we get data from water utilities, they make the definition themselves, and we get a record of pipes, for example, 100,000 of assets with different lengths.
Straight out of the GIS.
Yeah.
So it doesn't really know about the cast iron or ductile iron is made up of short lengths.
No.
So if it's repaired, you might have a new piece of pipe in the middle, but the rest of it is still old. But whether they've recorded that difference.
Actually, if the failure in the pipe happens because of, for example, corrosion in the pipe, even if they replace, for example, 1 meter segment of the pipe, the remaining part of the pipe is still corroded, and it's still old.
But is that one pipe or now 3?
In the middle.
Yeah.
And?
So what I'm saying is you've had 100 metres of pipe, you've replaced a metre of pipe in the middle with a different material, different age, different everything.
It's not a new pipe.
3 pipes?
No, that 1 meter pipe is not a new pipe. It's a part of a 100 meter pipe.
But it is in the future prediction.
Yes, and this is how it impacts, because it can be categorized as one failed pipes in our target, and when the model is trying to learn from which pipe is going to fail, which is not, it learns from the pipes. And to the best of my knowledge, if I have, for example, a 100 meters long pipe, segment of the pipe, and if I replace, for example, 1 meter of it, it doesn't make it like a new pipe.
No, it's definitely not a new pipe, it's still a risky pipe.
And it can be considered as a pipe with 99% old, 99 meter old, and 1 meter new. It's still similar to the old pipe. It doesn't reduce the likelihood of failure for that pipe.
Not for the rest of it, no.
Yeah.
Another thing is usually they do like for like. So, for example, they don't replace the metal part with the plastic.
PVC in a bit.
Yeah, metal pipe, yeah. Sorry, I just wanted to mention to participants online, if you have any questions, please raise hand. We'll open the floor for you as well. There are a couple of more questions in the room, but to those of you online, please feel free to let us know if you have any questions. Any other questions here?
This following question is regarding to the unbalancing data solving. Like that you mentioned that the solving to hide imbalancing data by using that algorithm that undersampling and oversampling, so that we creating some generic sampling data, the synthetic data.
In oversampling.
Yeah. So how we ensure that the synthetic data is actually represent the real world feeder rather than artificial bias?
In data science, nothing is guaranteed.
Yes.
Make sure is not a good word for that. We're trying to make the predictions better, improve the predictions by doing these approaches. There's no guarantee in none of them.
So we just try to using the algorithms to make
These approaches.
Approaches.
Yeah. By these approaches. It could be something like replicating the failed assets minority class, or, for example, if I have 2 minority instances in the space, I can generate and interpolate some new samples between these 2 existing samples. There's no guarantee to improve, but we have seen, not only us, over the past 2 decades, they have seen that it improves the quality of the predictions for a binary class machine learning model. Not only in the water engineering, not only in pipe failure prediction, and other prediction problems.
There was another question.
Thank you for your presentation. I have a question that's similar to other questions. When you talked about imbalanced data and oversampling or data augmentation, but I didn't understand what was your features when you used data augmentation. When you augment your data, I want to know what was your method and how you increase your samples.
When we talk about augmentation in weather and climate data, you mean weather and climate and soil data?
For example, in your diagrams, you evaluated the performance of your model. Yes, this one.
Yeah. For example, here the target is number of captured failures, number of correctly predicted failures in the validation time period. For example, if you have, for example, 10 years of data, I can train my model on 7 years of data and validate the model on 3 years of data that is unseen to the model. And I can predict the number of failures by replacing, for example, 5% of the assets. And I can see how many failures are captured by replacing only 5% of the assets, which is quite common for a water utility if they replace 1% of their assets every year. 5 years, which is too much. 5 years is like
very
5.
High. 1% is very high.
I know.
Thank you.
No worries.
There was another question.
But even 1% means replacing all the assets in 100 years.
Yeah, that's why it's high.
Yeah.
So I assume the data that you've used for the studies are in tabular format,
Yeah.
right? So I know that most tabular format data are suitable for the types of models that you have used, which are, say, classic machine learning models. Have you considered or have you seen in the literature review anyone comparing the performance of these types of models with more complicated models like neural network-based models, say, all these types of models?
Even neural network models are using tabular data to train. The only comparison I can do, or the improvement that I can do, is using tabular data and compare it with geodata, or geodatabases.
I mean the performance of the model itself, using the same type of data, but have you used
With neural networks?
Yeah.
In the literature,
What was the
in the literature, different kinds of models have been used, and they have been compared in different papers. Let me see. We have a review paper. In this paper, we have compared the efficacy or efficiency of tree-based models and compared them with other methods like neural networks, SVM, or other machine learning models in predicting the failure in pipes and assets condition maintenance of the pipes.
Okay, great. We have a couple of questions online. Could you,
6 minutes to go.
yeah, that's fine. Could you please turn get out of, yeah, how did we go to? Yeah, please, could you turn on your microphone and yeah, put your questions to Milad.
Who?
Hello, Edward.
Edward, yes.
Edward. Yeah.
Yeah, hi, can you listen to me?
Yes.
All right. First, hello, thank you so much for the presentation. It was very entertaining. The first question is, how do you handle data that may appear as outliers but are not considered so from an operational standpoint? I mean, particularly from the perspective of a pure data scientist. For instance, in district metro areas where, I don't know, we can have transient phenomena or high pressure scenarios, how do you integrate or manage this operational system information to ensure, well, it is not lost in all the data preparation process?
Yeah, actually, handling the outlier data is a part of data preparation that should be done through the domain expertise about the problem, about the data, things like that. And we have done in most of the cases. For example, in one of our case studies, we had 900,000 assets in a data set, and we find out that we have a lot of tiny pipes shorter than 1 or 2 meters. And by removing all those assets, we had, I think, 47,000 kilometers. By removing those pipes, we actually lost half of the data, but it was about only 2,000 kilometers. So we find out that by removing these tiny pipes from the data set, we can improve the quality, we can remove the numbers, and we can improve the predictability of the models. This is something that should be done in data preparation phase of the developing a model. And we have done it with different case studies, not only for one, but we did it using domain expertise and domain knowledge about the case study and the problem.
Okay, thank you so much.
No worries.
Slobodan.
Hello, Milad.
Hey, hello.
Yes, thanks for excellent presentation.
Thank you.
Just to state perhaps one more obvious thing why this is so very much important. So, London Underground study of greatest risks from flooding showed that pipe burst is by far the highest risk of flooding, even though London is under tidal influence and drainage system is not very good and they do a lot of pumping and all the rest of it. It's basically pipe bursts are the biggest threat from flooding for London Underground. There's just another interesting thing worth pointing out at the beginning. And now regarding what you described as potential for interesting future work. Now the thing is, even though this is all scientifically excellent and brilliant, basically what water utility managers want to see is how much money they are saving by doing one thing or the other. So I consider, and well, the proof of that is some years ago there was a project in the center called Whole Life Costing of Distribution Systems, which was looking at operational capital costs and, so what could be included here, for example, is on top of that is different types of damages that pipe bursts are making. So are you considering to include more thorough assessment of financial aspects of all of this, all in order to persuade different water utilities or consultancies to accept this technology as the way forward?
Yes, of course. In the papers, we focused on research aspects of what we have developed, but in the projects, real-world projects that we have done in data techniques, we were more focused on the economical impacts of replacing different sets of pipes by using these kind of models, and the tools that we have in our platform called Foresight give a good insight about different economical or financial aspects of replacing different percentage of the pipes for the water utilities. So we try to translate all what we find into water utilities language in a way that it's more tangible for them. Yeah, of course, yeah. We have done good jobs in that aspect as well.
John Steko, I'm afraid we have run out of time. May I ask you to please talk with Milad about your question. Unfortunately, the room is booked for another event, so we have to leave the room. Thank you very much for all of you attending in person and online.